For today's lesson, we're going to be dealing with exponential functions and their derivatives. So let's first review what an exponential function is. An exponential function is a function where we have a variable as an exponent. So you'll see exponential functions in a couple of different forms. The general form is f of x equals a to the x power, where a is greater than 0. So for example, an exponential function could be 2 to the x, or 1/2 to the x. This is an example of an exponential function. When you think about those graphically, there are two types of exponential graphs that we'll be dealing with. One is a to the x, and the other is 1 over a to the x. These two graphs have a couple of different names. We'll talk about this one as an exponential growth function, which means as x increases, the function grows exponentially. And you'll notice that I have an a y-intercept of 1 for this exponential function, because when I input 0 for x, we have an output of 1. Anything to the 0 power es uno. Next, 1 over a to the x is very similar to this graph. It's just an exponential decay function. That means as x increases, the function decreases exponentially. And you'll notice once again that we have a y-intercept of 1, because when x is 0, it is 1 over 1, which gives us our y-intercept. These two graphs, exponential growth and exponential decay, are the exponential functions that we have learned previously in previous courses. Now, very quickly, what are their domains and ranges? The domain of each of these functions is all real numbers. No matter what x value you plug in, there will always be an output. The range of each of these functions is from 0 to infinity. And notice I have a parenthesis around the 0 because 0 is not inclusive. It will never equal 0. It will become infinitely close but never equal it. Alright, for our exponential growth graphs, we have limits. These limits are as x goes to infinity, and as you remember, when we have a limit as x goes to infinity, that is describing end behavior of a graph. If I have an exponential growth function, meaning a function that looks like this, as x goes to infinity, the function, if it's exponential growth, goes to infinity. And you can see if we go to negative infinity, the function approaches 0. You can tell that it has a horizontal asymptote as x goes to negative infinity. It is 0. For a decay graph, those things just kind of alternate, because we have a limit as x goes to infinity approaching 0, and a limit as x approaches negative infinity, the function goes to infinity. So a couple of limits to describe end behavior. And without a calculator, we can graph these exponential functions. When you see a graph, there are a couple of things that you could do. You could make a table and plot points, or you could think about the transformations that are taking place. Let's go ahead and look at a table. If I plug in x in f of x, if I plug in this value, 0, 2 to the 0 power is 1, 1 minus 1 is 0. So our function value at 0 is 0. I just plot that point. From there, let's pick another value. Let's pick maybe -1. If I input -1 into the function, it would be 2 to the first power minus 1, which is +1. Let's pick another negative value to get a better idea. If I pick -3, -3 is 2 to the third power, which is 8 minus 1, is 7. So at -3, it is 7. That gives us a good idea of what's happening on the left side. As I go to the right, let's pick numbers over there. Let's try +1. This is 2 to the -1 power, which is 1/2, minus 1. 1/2 minus 1 is -1/2. Let's pick another value. Let's say we pick +3. +3, that would be 1/8 minus 1. It's going to get very close to -1 because 1/8 is close to 0, subtracting 1. And you can see by picking points, this is the look of our graph. It's an exponential decay graph because this negative exponent, it's the same as 1 over 2 to the x minus 1. It's an exponential decay graph. Now, to answer the limit, we want to know what this function approaches as x goes to infinity. As x goes to infinity, we see that the function approaches this value of -1. So our answer for our limit is -1. We will see exponential functions in many places. Population growth, bacteria growth, radioactive decay, half-life. So there are many applications that you will see exponential functions where we'll have to differentiate to find the rate. In order to do so, you'll need to know the derivative. And the derivative is on the board. It's the easiest one in the world to differentiate. The derivative of e to the x is e to the x. Fantastic. Makes life grand as long as you can remember this. We'll maybe work on a proof of this in class, but for now just have that memorized. The derivative of e to the x is e to the x, or the rate of change of e to the x is given by e to the x. Take a look at an example. If I have the function y equals e to the tangent x, this is something where we're going to have to use the chain rule. So remembering what the chain rule is, if I let u equal tangent x, then y is equal to e to the u. Now differentiating this, we have the chain rule. Going ahead and differentiating, we can see that the derivative of y with respect to x is equal to the derivative of y with respect to u multiplied by the derivative of u with respect to x. That's the chain rule, Leibniz notation. We'll simplify this. So the derivative of y with respect to u is simply e to the u, multiplied by the derivative of u with respect to x. The derivative of tangent is secant squared x. So now we'll just substitute back in our u, which is e to the tangent x, multiplied by secant squared x. And there's our derivative using the chain rule and the new derivative identity. For our first example, we're going to find the derivative given that y is equal to e to the -4x sine 5x. We're going to have to use product rule here since there is a product, and we'll also have the chain rule since there are functions inside of functions. So applying the product rule, we have y prime is equal to, remembering the product rule, first derivative of the second plus second derivative of the first. So the first is e to the -4x multiplied by the derivative of the second, which is cosine 5x, multiplied by the derivative of the inside function, which is 5, plus second, which is sine 5x, multiplied by the derivative of the first, which is e to the -4x, multiplied by the derivative of the inside function, which is -4. And then you can simplify from there to get this answer. I'm going to factor out an e to the -4x. And then inside I will have 5 cosine 5x minus 4 sine 5x. And that is your derivative. To find the absolute maximum value, remember, we're going to do the same process that we've done a million times. To find the derivative, find points where it's equal to 0, the critical points, place them on a number line, and find out where there's a sign change of positive to negative for a maximum. And then we'll go from there. So first thing we need to do is find the derivative. F prime of x is equal to, this is a product, so we'll use the product rule. First, derivative of the second, which is e to the negative x, multiplied by the derivative of the inside, it's negative 1, plus e to the negative x multiplied by the derivative of this, which is 1. Simplifying there just to make it a little bit easier, if I factor out a negative e to the negative x, I'll have an x and a minus 1. So I just factored that to get it in form so that we can actually find the zeros. So setting the derivative equal to 0 so that we can find critical points, we have negative e to the negative x equals 0, and x minus 1 equals 0. Well, this one is easy. X equals 1 is a critical point. This one, we can divide by the negative 1 and come up with e to the negative x equals 0, or 1 over e to the x equals 0. Now, based on what we talked about previously, we have an idea of what this graph looks like. If you think about this graphically, we know it's going to be an exponential decay function. So it looks something like this. Will it ever equal 0? And the answer is no, because there's actually a horizontal asymptote going to infinity on the positive side. So we know that there are no places where this graph equals 0. Therefore, our only critical point is x equals 1. Place that value on the number line. Now that we have 1 being a critical point, we're going to plug it into the derivative to find out whether it's positive or negative to see what our value will be. So we're going to find a value to the left of 1 is 0 is a good one to plug in. It's usually pretty easy. So f prime of 0 is equal to negative e to the 0 power. Anything to the 0 power is 1 multiplied by negative 1. Plugging in 0 into this, we will come up with a negative 1 multiplied by negative 1, which is a positive value to the left of 1. Plugging in a number greater than 1, we can pick anything. Let's try 2. So f prime of 2 is equal to negative e to the negative 2 multiplied by 2 minus 1 is a positive 1. This value is going to be a negative multiplied by a positive, which will give us a negative value there. Now, take a look at our value. We have a positive negative. That is the sign for a maximum value. Therefore, we know that x equals 1 is a maximum. Is it the absolute maximum? Well, in order to find out, you know maximums occur, absolute maximums that is, occur at critical points or endpoints. Since we do not have any endpoints of this function, we know the absolute maximum occurs at x equals 1. That value you can find by plugging it into the original equation, finding f of 1. So it's 1 multiplied by e to the negative 1, which is 1 over e. That is the absolute maximum value which occurs at x equals 1. The exponential function is used a lot in calculus. It models population growth, it models bacteria, it models a lot of real-world problems. So you'll see the exponential function quite a bit. So let's make sure we know what the graph looks like. So if we're going to look at the graph of y equals e to the x, its base is e. Remember, e is a number. More than 2, less than 3, 2.7-ish. If I graph this, it's going to look something like this. It is an exponential growth. We know the y-intercept, anything to the 0 power is 1. The y-intercept is 1. Take a look at what some limits could be. So before we get to the limits, domain and range. The domain is all real numbers. The range is from 0, non-inclusive, to infinity. Using these things, we can answer the asymptotes. The limit, as x goes to infinity. Well, what happens as x goes to infinity? The function goes to infinity. The limit, as x goes to negative infinity. As x gets very small, the function approaches 0. It doesn't ever get there, but it gets infinitely close, so therefore the limit is 0. There is a horizontal asymptote as x goes to negative infinity. So there is a horizontal asymptote here at 0. And that is the exponential function, the natural exponential function. Now that we know the derivative of e to the x, we can also talk about the integral, or the antiderivative. So the antiderivative should be relatively easy as well. If we know the derivative of e to the x is e to the x, the antiderivative is also e to the x. Make sure you remember to add the constant. That value is very important. So the antiderivative of e to the x is e to the x plus c. To find the antiderivative of this, which looks very, very complex, we're going to use antidifferentiation by substitution. So I'm going to let u equal x cubed. This little 3 is a little crazy on your notes, but just know that it's e to the x cubed. So if I let u equal x cubed, differentiating and using some knowledge, we know that the derivative of u with respect to x is equal to 3x squared. Moving things around using your algebra, we know that du is equal to 3x squared dx. We're almost there. We know that dx is equal to, or we'll leave it as x squared dx. We know that du over 3 is equal to x squared dx. This is going to help us greatly when we're finding the antiderivative. Doing so, I can rewrite this problem as the indefinite integral of e to the x cubed, and then have an x squared dx. This is what we like, because this part right here is equal to du over 3. So we know the antiderivative then would be e to the u du over 3, or taking that constant 1/3 out of the antiderivative, as we know that we can, it is 1/3 antiderivative of e to the u du. Now that we have it in terms of u, you can go ahead and use your antiderivatives. For indefinite integrals, we know the derivative of, or antiderivative of e to the u is e to the u. So this is 1/3 e to the u plus c. Plug back in our u, and it is 1/3 e to the x cubed plus c. This is our antiderivative using substitution. Whenever I hear find area under curve, I think definite integral. So I've set this one up already. We know the area under the curve is a definite integral from 0 to 1 of our function. Don't forget the dx. Now all we need to do is use the fundamental theorem of calculus to evaluate this number. This is a number, it's a definite integral. So we can find the antiderivative here. We know that the antiderivative, we can do it a couple ways. We can use substitution. We can simply evaluate it easily since we know it's undoing the chain rule. That's one way to think about it. I know that it's going to be e to the negative 3x divided by the derivative of the inside function, which is negative 3. And that will be evaluated from 0 to 1. Simplifying further, we have e to the negative 3 over negative 3 minus e to the 0 over negative 3. This value here is -1/3 e to the -3 minus anything to the 0 power is 1, but it's over a -3, so it'll be plus 1/3. Simplify this just a little bit to make it a little easier. We know it's equal to 1/3e cubed, negative exponent to the denominator, plus 1/3.